Understanding Cofactors. Welcome, everyone. Before we dive into our new topic, let's take a quick moment to recap what we've already covered. In our previous lesson, we explored the concept of the minor, which we denote as m sub ij of an element. As a reminder, the minor is simply the determinant of the smaller matrix that remains after you delete the specific row and the specific column associated with that element. Now, while the minor gives us a solid numerical value, today we are going to learn how to take this a step further. We are introducing the concept of the cofactor. The key difference here is that a cofactor doesn't just look at the value itself. It also assigns a specific algebraic sign, meaning it decides whether that value stays positive or becomes negative, based entirely on where that element is positioned within the matrix. So, stay tuned, as we will look at the exact formula for this in the next slide. One definition of a cofactor. Now that we have established what a minor is, let's move on to the formal definition of a cofactor. If we take an element located at row I and column j of a square matrix, which we denote as a sub ij, the cofactor of that specific element is represented by a capital A with the same I and j subscripts. So, how do we actually calculate it? It isn't just a new number. It is the minor we just learned about, but with one extra step. We take that minor and multiply it by a specific sign factor. This sign to factor is determined by looking at the sum of the element's row index and its column index. To put this into a formal mathematical relationship, we write a sub ij equals -1 raised to the power of the sum of I and j, all multiplied by m sub ij. To make sure we are all on the same page with this formula, let's break down the notation. A sub ij represents the cofactor of our element. M sub ij represents the minor of that same element. And that term, -1 raised to the power of I plus j, is what we call the sign factor. In the next slide, I will show you exactly how that sign factor works to either keep the sign the same or flip it. 2. Understanding the sign factor. Now that we have the formal definition from the previous slide, let's dive deeper into the mechanics of that sign factor. You'll notice the term -1 raised to the power of I plus j. This specific part of the formula is what determines whether the sign of your minor stays exactly as it is, or if it gets flipped to its opposite. The key to mastering this is to look at the sum of your indices. I plus j, it all depends on whether that sum results in an even or an odd number. Let's look at case 1, when I plus j is an even number. If you add your row and column indices and get an even result, for example, 1 plus 1 equals 2, or 1 plus 3 equals 4, or even 2 plus 2 equals 4, then -1 raised to an even power simply equals +1. In these specific instances, the cofactor is identical to the minor. The sign doesn't change at all. Now let's consider case 2, when I plus j is an odd number. If your sum is odd, take 1 plus 2 equals 3, or 2 plus 1 equals 3, or 2 plus 3 equals 5, for instance, then -1 raised to an odd power results in -1. In this scenario, the cofactor becomes the negative of the minor. You are essentially flipping the sign. To make this much easier to visualize during your calculations, you can use what we call the checkerboard pattern. For any 3x3 matrix, you don't always have to do the addition manually. You can simply remember that the signs follow an alternating pattern, starting with a plus in the top left, then a minus, then a plus, and so on, just like the squares on a chessboard. In the next slide, we are going to put this theory into practice with a concrete, step-by-step numerical example to see this pattern in action. 3 step-by-step example. Let's look at this 3x3 matrix, which we will call matrix A. It contains the following elements. In the first row, we have 2, -3 and 5. In the second row, 6, 2 and 4. And in the third row, 1, 5 and 7. First, let's walk through example A, where we want to find the cofactor A sub 1, 1. This refers to the element in the first row and first column, which is the number 2. Step 1, we identify our indices. Since we are looking at the first row and first matrix column, I equals 1 and j equals 1. Step 2, we need to calculate the minor, denoted as M sub 11. To do this, we mentally delete the first row and the first column of our matrix. This leaves us with a smaller 2x2 matrix consisting of the elements 2, 4, 5, and 7. We find the determinant by calculating 2 times 7 minus 4 times 5. That gives us 14 minus 20, which results in a minor of -6. Step 3, now we determine the sign factor we discussed in the previous slide. We add our indices together. 1 plus 1 equals 2. Since 2 is an even number, our sign factor will be +1. Step 4, finally, we apply the formula. We take our sign factor, -1 raised to the power of 1 plus 1, and multiply it by our minor, which is -6. 1 times -6 leaves us with a final cofactor, a sub 11 of -6. Now, let's try something slightly different with example B to see how the sign changes. We want to find the cofactor A sub 12, which corresponds to the element in the first row, second column, that is -3. Step 1, our indices here are I equals 1 and J equals 2. Step 2, let's calculate the minor, M sub 12. Again, we delete the first row and the second column. This leaves us with the elements 6, 4, 1, and 7. Calculating the determinant, we get 6 times 7 minus 4 times 1. That is 42 minus 4, giving us a minor of 38. Step 3, let's check the sign. Adding our indices, 1 plus 2 equals 3. Since 3 is an odd number, our sign factor will be -1. Step 4, applying the formula, we take -1 raised to the power of 1 plus 2 and multiply it by our minor of 38. -1 times 38 gives us a final cofactor, a sub 12 of -38. Now that we have understood the theory and the checkerboard pattern of signs, let's put everything into practice with a concrete example. Notice how the value of the minor stayed positive, but the cofactor became negative because of the position of the element. This brings us to our next slide, where we'll look at why this sign change is so important in real-world applications. 4. Real-world analogy, the weighted contribution. Think of a cofactor not just as a calculation, but as a weighted contribution within a larger system. In many complex fields, like physics or economics, the impact of a single variable isn't just about its size or magnitude, which is what the minor represents. It also depends on its orientation or direction, which is represented by the sign. To make this even clearer, imagine you are looking at a financial ledger. A positive value might represent a gain or profit, while a negative value represents a loss. Similarly, when we are calculating the determinant of a matrix, the cofactor tells us whether the value of the minor is going to add to or subtract from the total final value. Now, I know that all the formulas and calculations we've just gone through might feel a bit abstract. So, let's take a moment to step back from the numbers and look at the bigger picture with a real-world analogy. Understanding this concept of direction will be very helpful as we move into the next slide, where we'll discuss some common pitfalls to watch out for during your calculations. 5. Common mistakes to avoid. First, a very common mistake is confusing the minor with the cofactor. It is quite easy to do all the hard work of calculating the determinant of the smaller matrix, the minor, and then simply forget to apply that sign factor we discussed earlier. To prevent this, I want you to adopt a specific mental workflow. Always follow this sequence. First, find the minor. Second, determine the sign. And third, arrive at your cofactor. If you skip that middle step of checking the sign, your result will be incorrect. Second, watch out for sign errors when you are dealing with negative minors. This is a tricky one. If your calculated minor, let's call it M sub ij, is already a negative number, for example, -6, and your sign factor for that position is also -1, remember that a negative times a negative results in a positive. So, -1 multiplied by -6 becomes +6. Don't let the double negatives trip you up. Finally, be careful with incorrect index summing. When you are calculating that exponent, remember that we are adding the row number and the column number, the I and the J, not the actual values of the elements sitting inside the matrix. You are looking at the position, not the content. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to make small errors that can lead to the wrong final answer. Keep these 3 points in mind, and you will be well on your way to mastering cofactors. Let's move on to our final summary of the key takeaways. Key takeaways. First and foremost, remember that a cofactor is simply a signed minor. It isn't a brand new value, but rather the minor we calculated earlier, just with a specific sign attached to it. To keep your work organized, always rely on the mathematical formula. A sub I, j equals -1 raised to the power of I plus j, multiplied by the minor, m sub I, j. This formula is your roadmap for determining that sign. As we discussed in the previous slides, the behavior of that sign depends entirely on the sum of your indices. If the sum of the row and column indices, I plus j, results in an even number, the sign of your minor remains exactly the same. However, if the sum, I plus j, is an odd number, you must reverse the sign of the minor. Finally, a great way to double-check your work is to remember the checkerboard pattern we looked at earlier. The signs of cofactors in a matrix will always follow that alternating pattern, always starting with a plus sign at the very first element, a sub 1, 1. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways to ensure you have a solid grasp of the concept. If you can master these points, you'll be well prepared for more complex matrix operations in our next session. Great job today!